Our aim today is to construct the Lebesgue measure using the Riesz representation theorem. So, recall that the Riesz representation theorem tells you that a positive linear functional on the space of continuous functions with compact support on a locally compact Hausdorff space X, right. This space is called CCX. If I have a positive linear functional on CCX, it is given by an integration against the positive measure. Not just that, so the theorem comes with host of other results, that you get a sigma algebra which is bigger than the Borel sigma algebra on X, and there are some regularity properties which are very similar to what we have seen for Lebesgue measure, right. So, what we will do is we will use continuous functions with compact support on Rk to define a linear functional. This is actually the Riemann integral of the function, and that will give us a measure which is the Lebesgue measure. And certain regularity properties immediately will follow, because Rk has the property that a very open set in Rk is a sigma compact set. On such spaces, if you have a measure which is reasonable in the sense that it has finite measure on compact sets, then it is automatically regular. We have already done that. So, some of those properties will follow immediately. Okay, so let us start. So, I will recall some notation. So, remember the set Pn. Pn was the set of all those points in Rk, x1, x2, etc., xk in Rk, where each coordinate was 2 to the minus n times an integer. So, each xj was 2 to the minus n times m for some m in integers, right. And we had omega n to be the collection of 2 to the minus n boxes. So, remember these were cubes with side length 2 to the minus n. Remember that was a product of intervals of the type alpha beta. It was open on the right hand side, remember that, 2 to the minus n boxes with corners in Pn, right. So, in the real line case, we have 1 here, 2 here, and so on. You divide this into half and so on, and we are looking at intervals of this kind. Okay. Similarly, for R2 and R3 and so on. Okay. So, we had 0 0, 1 0, 1 1 and 0 1 0 or 0 1, and then we divide this into 4 equal parts, and this area, right, which is open on this portion is not there. So, such things are called cubes with corner in coordinates in Pn. So, we use this to construct a linear functional. So, construct a linear functional on Cc of Rk as follows. Well, how do we do this? We do this at nth level and then take limits. So, let lambda n of f. So, f, I am taking f in Cc of Rk. So, it is a continuous function with compact support. Lambda n f is simply 2 to the minus nk. So, 2 to the minus k is the volume of a 2 to the minus k box, okay, times the sum of x and Pn. Okay, so, I use a different p. So, Pn. So, Pn is this collection of numbers or coordinates, and you sum up f of x. Okay. This makes sense. So, remember f is compactly supported. compactly supported. So RHS is a finite sum. RHS is a finite sum. Okay. But what exactly is this? Well, this is actually a Riemann sum. So let us look at one a particular case in the real line, so that this is much clearer. So I take 0 1. So let me write the unit interval to be slightly big, and then you go to nth level. So then I have 1 by 2 to the n, 2 by 2 to the n, etc., etc. 1 is 2 to the n by 2 to the n, something like this, right? And you are looking at intervals of this form, etc., etc. What are we doing? So let us take a function which is compactly supported inside 0 1. Okay, so I take 0 and 1, and I have some function here. Okay, so let us say it's supported inside 0 1, and we are forming this sum. Okay, so here the k is 1 because the dimension is 1. So I am simply looking at 2 to the minus n times sum over x in Pn f of x. What is this? Okay, so let us rub this off. So we are looking at k equal to 1, and we are looking at 2 to the minus n summation x over Pn f of x. Well, we don't have to sum over all the points in Pn because f is supported in 0 1. So we will look at only this area, this interval. So what is this? This is equal to 2 to the minus n times, well, I have f0, right? That is a point in 0 is a point in Pn. Then I have f of 1 by 2 to the n plus etc., etc., right? F of 2 to the n minus 1. 2 to the n by n, 2 to the n, right? F of 1, maybe f of 1 is not included, the one before that is included. Okay, so let's not write this point. I'll just put a star to indicate that we are choosing the point here. Okay, all right. So what exactly is this? So you look at each interval, right? Each interval has length 2 to the n. So here length of each interval is 2 to the minus n. So you are multiplying by the length of the interval and a value of f inside that interval. So that is a Riemann sum. So the above is a Riemann sum. The Riemann sum, right? So in the Riemann integral, remember we divide this into intervals, and then we choose. So ith interval we choose the supremum and the infimum of the function, and then multiply by the length of the interval the value of either the supremum or the infimum, right? And this sum we have seen here will be something in between. So the lambda n f is simply bigger than the lower sum and less than or equal to the upper sum, right? In the case of real line, and the similar definitions for Rk will make sense. What is P? P is the partition of the interval we have here. Okay, so and as length of P goes to 0, we know that this will converge to so this and this will converge to the Riemann integral of f. Riemann integral of f, because f is continuous, compactly supported, so Riemann integral exists, it will converge. So similarly the limit of this will exist, and that's precise, and that's also the Riemann integral of f, right? That is the definition of our linear function. So define define lambda f to be equal to limit n going to infinity lambda n f. So this is precisely the Riemann integral of f. Okay, we are not going to write it that way, but this is what happens, right? This is true in Rk as well, in higher dimension as well, if you define the Riemann integral using the boxes instead of intervals. Okay, so this is now, it's clear that it is clear that lambda is linear. Lambda is linear. Well, why is that? Because if I take f and g in Cc of Rk, then lambda n of f plus g. So what is lambda n of f plus g? This is the sum, right? This is the sum, this sum. And if it is f plus g here, then it becomes sum of two things. And so lambda n of f plus g is lambda n f plus lambda n g. So if you take limits, these two things will go to lambda of f plus g, right? That is the definition of lambda, and lambda f here, lambda g here, and so on. Okay, if you multiply by a constant, the constant will come out. So lambda is linear. Lambda is clearly positive. Clearly positive. Why? Because if f is positive, because f is greater than or equal to 0 implies each lambda n of is greater than or equal to 0, because you are adding the values of a positive function, right? Here these things are positive, so when you add them you will get positive numbers, and so it's a positive linear function. Okay, so hence, so to conclude, what we have done is lambda is a positive linear functional, because it takes values in the real line or in the complex plane depending on where f takes values. Lambda is a positive linear functional on the space Cc of Rk. So remember, Rk is a locally compact Hausdorff space, etc. So Riesz representation theorem applies. Hence by Riesz representation theorem, so our RT is Riesz representation theorem, we get a measure which we call M and a sigma algebra script M. Okay, so recall that the sigma algebra script M is such that the Borel sigma algebra is contained in it, right? That comes from the theorem, and we have some regularity properties. Okay, so now we prove all the properties which we had stated in the last lectures. So we will start from A. So the first assertion A. So I will write down what it is, and then we will. So A, the first assertion was that if W is a K cell, so K cell was, remember, is the product of intervals, right? Rectangle in our earlier notation, it is product of intervals. Then the measure of the W is the volume of W. Okay, so that's the first thing we want to prove. So let us prove that. So we start with an open cell. Let W be an open K cell. So it's a product of open intervals, right? Let ER, so we have to use the definition of the positive linear functional to conclude this. So let ER be the union of those boxes in omega r. So remember, the side length here was 2 to the minus r, right? Whose closure lie in W. So let ER be the union of those boxes in omega r. So remember that side length is 2 to the minus r, whose closure lie in W. So, we are looking at some W like this, and ER is the union of boxes in omega r's, right. So, omega r gives me a partition of the space with cubes whose corners are in a certain prescribed set, which we called PR, and this will give me some. So, we are looking at the union of boxes in omega r. So, we are looking at some boxes like this, okay, not the ones which go out, but whose closure lies inside. So, remember the W is an open cell. So, the boundary is not included. So, when I take the closure, I do not want to touch the boundary. So, things which are strictly inside. Okay. So, now by Rougeon's lemma, so by Rougeon's lemma, there exist f sub r, which are continuous functions with compact support, and they are between 0 and 1. So, these are all part of Rougeon's lemma statement, you already know that, such that chi E bar closure is less than or equal to Fr less than or equal to chi W, right, which means that on ER it is 1, outside W it is 0, right. So, I am looking at something which is 1 on these boxes and maybe on a slightly bigger set, but it is 0 outside W. Okay. So, these are functions given to us by Rougeon's lemma. So, put G sub r equal to maximum of F1, F2, etc. up to Fr, right. For each r I have F sub r, I am taking the maximum up to r F sub r, that I call GR. Okay. So, then volume of ER, okay, is less than or equal to lambda of Fr less than or equal to lambda of GR less than or equal to volume of W. So, let us try to understand what this is. Volume of ER is simply the sum of the volume of the each boxes, right, because they are disjoint. So, you simply add them. Now, so let me draw one more picture to make this this clear. So, let us say this is my W, this is my W. Let me use another color for the boxes inside. So, I have some boxes here, okay. They are disjoint because you are looking at product of left hand closed and right hand open sets, right. So, they are disjoint, and that this is what forms, if I take the closure, I will get ER closure, okay. And well, what is FR? FR would be something which is 1 on all this set. So, it may be 1 on a slightly bigger set as well, okay. So, FR is something which is 1 here, equal to 1 here, and Fr is of course 0 outside W, okay. It is a compactly supported function. Alright. So, now it is clear that, so what is volume of ER? Well, volume of ER would be the sum of those things, right, sum of the boxes. So, you look at these boxes, you add the volume of each of them. That is same as putting 1 here and calculating lambda Fr, right, that is the volume. But it is 1, Fr is 1 on a slightly bigger set. So, there are more things you are picking up. So, this is obviously bigger than volume of ER, and GR is of course greater than or equal to, right, GR is greater than or equal to Fr. So, GR minus Fr is positive. So, lambda of this is also positive, and so we have this inequality. And the other one is clear because GR is 1 only on the union of sets coming from E1 to ER. After that it can be less than 1. So, volume of W will be much bigger than lambda of GR, okay. So this inequality is easy to see, but that is very crucial for us in proving that measure of W is same as the volume of W. So now let R go to infinity, let R go to infinity. Well, what will happen to volume of E sub R? Well, this will have to go to volume of W. Well, why is that? So let us recall what ER is. ER is the union of all the 2 to the minus R boxes inside W. Remember that W is a disjoint union of boxes from union of omega, right. So this is because W is a disjoint, because any open set is a disjoint union of sets from union omega R, right, are equal to say 1 to infinity or 0 to infinity. So ER as R goes to infinity, so this may be ER, and when you go to ER plus 1 you will pick up more smaller ones, right, and so on so forth. So I can call this ER plus 1 and so on and so forth. So you will fill up other places by taking R's bigger and bigger, because the side length becomes smaller and smaller, and W is finally the union of those things. So this follows. So on the left hand side, so if you keep this in mind, on the left hand side this I know converges to volume of W. Okay, and lambda gr, so what happens to lambda gr? Well, lambda gr is integral of gr dm by, this is by the Riesz representation theorem, right. We have the measure m, and gr is a compactly supported continuous function, so it is measurable, and lambda is given by that measure m. So this is the Riesz representation theorem, and this converges to, as R goes to infinity, will go to measure of W by monotone convergence theorem. Okay, why is that? Because gr increases to the indicator function of W. Well, let us see why. What is gr? Gr is maximum of f1, f2, fr and so on. So gr, so remember f1 would be 1 on 1 boxes, f2 will be 1 on half boxes, and f3 will be 1 on 2 to the minus 2 boxes and so on and so forth. So when I take gr is the maximum of those things. So it will be 1 on a large number of boxes completely inside W, and W is disjoint union of sets from this. So as R becomes bigger and bigger, gr becomes 1 on a larger and larger set, which finally becomes W, right, finally converges to W, and so gr will converge to the indicator of W. So by monotone convergence theorem, lambda gr will converge to MW. So from here we get, so let me write here itself, so we get volume of W is less than or equal to measure of W, because the middle term goes to measure of W, less than or equal to volume of W, because this side there is no dependence on R. Okay, so this implies that volume of W is same as measure of W. So for every open cell, every open K cell. But this is true for all cells. Why? Because now every K cell is a decreasing limit of open K cells. The decreasing limit of open K cells. Okay, so what does that mean? For example, if I take for K equal to 1, dimension 1, if I take a cell like this, let us say closed interval, and this is of course the intersection of, this is the intersection of, you look at intervals of this form, right. So, you can look at a minus 1 by n, b plus 1 by n, you take the open interval and then take the intersection, right. This is equal to the closed interval a b, but these are open K cells, right, they are open intervals. Similarly, if I have one side open, well then what should I do? I will look at intersection n equal to 1 to infinity, open at a minus 1 by n and open at b. So, these are open cells and intersection would be equal to closed at a, open at b. So, if I know the measure of this things, since this is a decreasing sequence and the measures are finite, I can apply the theorem we know. If I have a decreasing sequence of sets, MEN will converge to ME, right, if En converges to E or En decreases to E, provided one of them has finite measure, right. So, that you apply. So, hence we get volume of W. So, that also of course will converge, volume of W will become a, so it is like volume of AN. So, let's look at this again, volume of A minus 1 by n to B plus 1 by n. This is nothing but B minus A plus 1 by 2 by n, and of course that converges to B minus A, right, whatever the interval is, which is the volume of that interval. So, we get volume of W equal to MW. Well, MW because M is a measure, and if you have a decreasing sequence of sets, you know it converges. So, volume of W equal to MW for every K cell W. So, that proves one assertion. So, let me write down the second one. This we already know. Okay. So, B, the assertion B was the sigma algebra M we got contains the Borel sigma algebra. So, this follows from Riesz representation, statement of Riesz representation theorem itself. Also, a set belongs to M if and only if there exists a set A which is F sigma and a set B which is G delta such that A is contained in E, contained in B, and M of B minus A is 0. So, this we already know, right. So, this follows from this, we know from the Riesz representation theorem and the consequences. Right, because RK is sigma compact, RK is sigma compact, and any open set in RK is also sigma compact, any RK is sigma compact. So, if we have the second assertion that any open set in RK is sigma compact, then the consequences of the Riesz representation theorem, which we looked at the finer properties, will also be true. So, this follows immediately from whatever we already know. More importantly, it also follows that M is regular. So, Riesz representation theorem gives you outer regularity and inner regularity for sets with finite measure, but that we have been able to change if the space is sigma compact, any open set in RK is sigma compact. So, we can use the second consequence of the Riesz representation theorem to say that any reasonable measure is regular. So, this directly follows from Riesz representation theorem. Okay, so let us stop here. We have just constructed the Lebesgue measure using the Riesz representation theorem by constructing a positive linear functional on CC of RK. what we have just proved tells us that it is actually the sigma algebra we obtained from Riesz representation theorem is actually the Lebesgue sigma algebra, because it's the sets in the sigma algebra differ from Borel sets by a set of measure 0. So, it is the completion, and it equals the volume of each K cell. So, we have equality there. Now, we will look at other properties, that it is translation invariant, and we know that this is the unique, well, we will also prove that this is the unique translation invariant measure on RK, which gives finite measure to compact sets, and we will see how how the linear transformation affects the measure. So, remember, a constant will come out. That constant is actually the determinant, which we will prove later on. Right now, we will prove that if you take a linear transformation, Lebesgue set will be mapped into a Lebesgue set, and its measure is a constant times the measure of the original set. Okay.